So you update the theta here by combining alpha and delta theta. So there are issues here. First question is this: is the gradient direction is always the optimal one? So that's one question, right? The second question is, how do I choose the step size? So there are multiple ways for choosing to answer these two questions. So the shorter answer is this: the gradient descent may not be optimal solutions in general, right? So you choose delta theta to be opposite the gradient of loss function with respect to theta here. And that's one choice. In fact, this type of methodology called steepest gradient descent. Steepest gradient descent. Because that's the steepest direction. But in general, may not be the best directions of that. And there's a other methodology, something called Newton's method here. They choose this delta theta here. In general, is equal to the gradient of your theta here. But then you're going to rotate that by another matrix here. Another matrix. Let's call it H here. And that would be the, you have calculated gradient direction, and then you rotate that by another matrix. And then people believe that this new direction is actually better. So for instance, there's a method called Newton's method here. And in that case, I will choose my matrix here. Let's call it A here, just general here. I choose my matrix A here, choose A here to be something called my Hessian, to be a secondary derivative of this loss function with respect to parameter theta here. That's my Hessian here. And then I take an inverse of the Hessian here. And that would be the matrix I use to rotate my gradient direction. So I'm going to rotate a little bit, not exactly point toward the steep descent direction, but slightly shift direction here. And this is something called Newton's method here. And then you can show that this method here in general is much more efficient than this method here and the steep gradient descent methodology. And this is, in general, people call this kind of called a second order methodology. The reason for the Newton's method works is this. You can think about this. Suppose now you have your loss function here. Is functions of parameter theta here. So now you think about this. Suppose right now, let's say I'm going to view my theta here to be my current values of theta here plus a small perturbations of that. Okay, suppose that's the case. If theta here is equal to the small perturbations of that. The question you can see within a small range of that, what this loss function look like? Well, you can always approximate that function using Taylor's expansion. So that will be the constant term, and then next will be the linear term. So linear term, that will be the gradient of the loss function at this guy's here. And then about this little perturbation direction of that. So that's the linear term. And also if you want to make it more precise, more accurate, and then you go to the next step. So that would be the second order approximations of that. So within the second order approximation, and you have the you have this terms here to be delta theta transpose, and then you have the second order that's called Hessians of this matrix here times delta theta here. That's the Hessian here is equal to second derivative of this with respect to the parameters. Pen doesn't work here. Hessian here is equal to second order respective parameters. Oh, I don't know reason my pen doesn't work anymore. Okay. So this is called a second order approximations of this loss functions of that. So I'm going to put approximation signs of that. Okay. So within this approximation, you can say, well, which direction delta theta can minimize this overall approximated functions here. And you can see that the best directions here will be this Newton's direction I wrote down here. So there's a reason that people choosing this type of thing is because exactly this reasons of that. All right, so I will not talk about details of this so-called the Newton's methodology because this is called a second order method, but I just want to mention that. So the steepest gradient descent, this is the focus of this class. The method we focus on is not necessarily the only method here. There's also other methodology. However, in general, the Newton method, even though it's more accurate, but however, it's more expensive to calculate because you know to calculate this delta theta here, and then we need to calculate the Hessing. But the Hessing is a matrix. In general, it's more expensive to calculate that. And you can see here, I need to involve this inverse of the Hessing as well. So that is even more expensive. So in general, the idea is very nice, but in practice, it's not so easy to implement that. All right, so that's what I want to say here regarding the gradient methodology. And as I mentioned in this slide of that. All right, so next what I'm going to do here, I'm going to talk about it within MSE. How do I actually calculate this gradient of this loss function with respect to theta? Because without being able to calculate that, I will not be able to kind of update my parameters. So that's really it's kind of critical that we will be able to calculate this gradient respect to loss function. So next, let's go through a little bit few steps to find out how do I actually calculate this gradient respect to parameter theta. Once I do that, and now I will be able to implement this gradient descent methodology.